Okay, so I'm going to stop about 50. Okay, so that was the introduction. So now we go to the more fun part, so the transmission of optical fiber. Okay, so optical fibers, so basically, it's basically transmission of light, right? So it's kind of fun because you can actually you can bend an optical fiber, and there's a lot of gadgets which have been built with optical fibers, apart from the laser, of course. But we have all these Christmas tree with optical fibers, because of the property that you can actually bend. You can bend light. That's not so straightforward because if I have a beam like this, it's very hard to bend this beam. I can do it with electrons, okay, because electrons are sensitive to an electric field. Okay, so if I have a beam of electrons, I can put an electric field and change it. And that's how the CRT television, the old television used to work. So you have a beam of electrons, and then by changing the voltage, I could actually steer the beam where I wanted and produce my signal, actually visuals. But you see, you try to do that with light, because it's not affected by an electric field. With the fiber though, you can actually bend the fiber, so I can actually bend the light other way. So that's based on that phenomenon which is called total internal reflection. The next slide. Again, so fiber characterized by very low loss, 0.2 kilometers, and I was saying before, large bandwidth. So imagine a signal can go 150 kilometers without amplification. Possibly something so far without an amplification. Then that's not even remotely possible what you can do with an electrical wire. I'm just introducing here some basic optics definitions which we will use later. So C0, this is the speed of the velocity of light in the vacuum, right? So you can understand the vacuum. It's about 300,000 kilometers per second. And any kind of light will have that speed in the vacuum. So the sun, that's the speed light out from the sun, so it takes seconds and so on. Now this is related to the frequency. So I was showing before how the wavelength size goes in one direction and the frequency increase goes in the opposite direction. So there is a pretty much straightforward relation, which is the frequency, sorry, the wavelength multiplied by the frequency gives exactly this value. Another formula is interesting, is this one. So basically, the frequency is measured, we measure the frequency in hertz, we measure this in meters, or in fact we measure this in nanometers. So when you build elements and you start doing wavelength multiplexing, sometimes you don't use frequencies, but you start using wavelength. This is just a simple formula that converts. Like if I want to know how much space do I need in the fiber to get, in the bandwidth fiber, to get 100 gigahertz. So that actually depends on what's the central frequency is. Yeah. So if I use a laser at 1450, you'll occupy a certain part. If I want 100 gigahertz, if I use it on another part of the spectrum, it will be a different type. This is the formula for a traveling wave with this kind of frequency. If you do this on any simulation or computer, you see the solution is something that away. And see, this is quite important as well, is that the velocity of light in a medium is the refractive index n. So the speed of light is constant, agree with that? It's constant and it's equal to this only if it's in the vacuum. Okay? So the speed of light changes actually depending on which material is going through. And this is going to be a huge impact. Okay? And there are some people who actually manage to, not to stop the light, one with optical memories. The problem with the problem is that with an electron, you can stop the electron, stop it there in the memory, and then bring it back over. With light, you can't stop it. You won't stop it. But then, you can use tricks to slow it down. Other stuff useful quantities. So decibel is what is used in optical communication. It's the same in wireless communication. So for who doesn't know, it's basically the reason is that power loss follows an exponential law. And the ranges of the power you can use is basically extremely usual. It will be 100 or millions of times different. So I can work with a signal which is 1 watt, for example, and then I can as well work with a signal which is like 100 million times weaker with that. So it's very hard to put numbers, when you have so many zeros. So the DB is actually quite good for that. And it's quite good because basically it's logarithmic. So anytime I have increased by 1,000, I just have to sum up by 30 in terms of degree. So that's the rule. So this is the definition of degree. So the base definition used for ratio between powers actually. Okay? So if I have a transmitting power, or T, sorry, Pt, this is my receiving power. So this is the power I transmitted. Could be wireless, could be optical. This is the powers I receive. It's probably a huge difference on that. But probably there's 100 millions time or millions time difference. See, if I go to this formula, then this becomes a number which is much more manageable. Okay. So as I was saying, 60. So a million times bigger basically means 60 degrees. That's much easier to work. The other thing is that I said this value is basically dimensionless because we have defined as the ratio between two similar dimensions. Okay. It's a dimensional. However, there's a trick. Right? So if I want to transmit, so if I have a receiving power which is 10 minus 6 milliwatts or something like that, so it's very hard to work with this number, but I can still say that it is minus 60 dBm. Okay? So there's a trick, that's why there is a trick. So I can use 1 milliwatt as a reference number. Okay? So imagine I put 1 milliwatt here. Then I can use, basically I can actually say that this is the transmitted power as a certain number of watts. Okay? So basically means I can use the dB for things differently than just a ratio between transmitting and receiving power. I can use the dB scale also for just for transmitting power itself. I just say this is 30 dBm, for example, which basically means it's 30 dB above 1 milliwatt signal. And that's something you will be very familiar with. So another reason is that it makes it easier to make some kind of calculation. For example, if I double the power, I just have to do plus 3 dB. If I want the power 4 times, it's plus 3 is plus 6. The same, if I do 10 times, I just do plus 10. Okay, so if I want to do 1,000 times, I do plus 10, plus 10, plus 10. So it's easy to manage. That's it, if I want to do. So here is the phenomenon I was talking before is called total intelligent reflection. So this is a geometrical approach. It's a geometrical explanation of how fiber works. So consider there's two different mediums and they are refractive index N1 and N2. The easy way to imagine is that one is water and the other one is air. Now if I have an incident ray from this surface to this surface, what will happen is that there will be a mismatch somewhere here. So this is a bit like imagine if I have a mirror and I put this was a mirror and I do this way. Then I have a ray, incident ray, and the other way, one ray will be deflected. This will be deflected. Now there is another part of the ray which actually will go through. Okay. For example, this exactly effect until this towards the window. Okay. One part will be reflected that way, you might not see now, and one part will go through the window. Now when the two medium are different, these angles are not the same. And these are the relations drawn by those numbers. So the refracted ray is basically has always the same angle to the incident ray. And that's the way it is. The refracted ray though has a different angle. So that's the important part. Now, if I choose these two mediums, right, so that the refractive index N1 is higher than N2. Now, indicatively, you can imagine that sometimes density a denser medium has a higher refractive index, but it's really, don't take it to account. Now, if I use this medium where this one is a higher N than this one, then okay, this is refracted the same way, but this is refracted at a higher level. So this one is closer to the surface than this one is. If I keep doing that, keep putting this higher and higher, this comes lower and lower. At a certain point, we have that this angle is still not touching here, so it's still not totally parallel, but this one has become parallel. Okay? And this is called the critical angle. So the critical angle is basically given like this. It's the time at which this refracted ray doesn't go in the single medium. Okay? So that means if I tweak it a little bit more up, then even the refracted medium is basically inside here. Okay? Now that's called total reflection. That means if I shine a light with this direction here, this medium won't get any light. So basically, that means there's no loss at all on this medium. Now imagine if I put the N2 down here as well, then you have the light basically will be bouncing up and down, or will never hit the medium. And that's actually how the optical fiber works. Right? So I put a laser here, and then it keeps bouncing, and just go. Okay, I will just go with the slides. So basically, that's how you do the fiber. You take two pieces of glass. One glass has a refractive index M1, and the other one has a refractive index which is slightly smaller than this one. And then I put a laser here. So I was saying before, it really depends on what angle you are shining the light. Right? If this thing is a kind of a too small angle from this point of view. So basically what happens is that it gets inside. At this point, it won't have total reflection because the incident angle is too high. So basically, it means some part will be reflected and some part will be refracted. Now, the refracted part is lost. Okay? So basically, there is some part of the power which basically leaves the fiber. That's gone. And then as you bump again, so this is diminishing power. You bump again, you lose another bit, you lose another bit, you lose another bit. By few number of bumps, you've lost it. So if I shine from this angle, basically the light is not going to propagate. So I have to propagate between this critical angle. So if this is the fiber, if I put the angle this way, I probably lose it. If I twiddle it within the critical angle, then the light will remain in like forever. Apart from what I lost it. Okay, so that's what you do. You shine the laser at a certain angle, and then will work. Now, there is actually another difference on which angle you actually shine the light. So I have two now here. The red one, margin, is the critical angle. Okay, so it will be reflected this way. And then there is a green one, which is a higher angle, so it's even better, let's say. The only thing is that this will have a different propagation. Okay? So it will actually have different kind of propagation. And we'll see that these are actually called modes of propagation. And I think I said it pretty much. So the common acceptance is basically the angle at which I can shine light in the fiber, and I will be sure that it will remain inside the core of the fiber. It's called the cone acceptance. And that, of course, is a cone because I can actually twist this all over the part as far as the angle remains the same. And that's basically the formula which tells me how you get the cone acceptance. I think that's probably it's about 50 minutes, so we won't do it too much. Yeah.
Does the critical angle limit the curvature of the fiber, or does the fiber break itself?
Well, there is another thing as well, which is the will limit as well, how much you can bend the fiber. Yeah.
So the green one you get to bend it more, right?
Yeah, well, in theory, yeah. In practice, we'll see that. There will be two kind of fibers. One is called multiple fibers, which basically this is allowed to happen. And another fiber which is called single mode fiber, which is built in a way that there's only one mode can propagate. Right? So basically, if you have a multiple fiber and you bend it, you might lose some part of it, and you might not lose other ones. If you have a single mode, you bend it. It's basically, if you have a laser on one side and a detector on the other side, you can start bending and you see that there's no difference. Up to a certain point, where you basically, you lose most of the fiber. Cool. Anything else? Another question? I forgot to say at the beginning, but you can ask us.
This is kind of, I don't know if it's really on topic of this, but you know when you have a fiber optic and you look at it from the side and you can see the light on the side of it.
Yeah.
Is that escaping light? I assume.
Well, how do you know that?
We're talking about cheap fibre optics that come in those Christmas trees that are made out of plastic. That's not real fibre optic.
But real life fibre optic, you won't be able to see anything in the side at all.
Because actually, the first experiment of light propagation was in 1800. And I think this guy with the propagation, he had basically kind of a water fountain with a water jet. And basically, he made the whole room empty. And basically was shining light inside the water jet. Now the water would kind of remain inside the jet. So basically, we wouldn't shine out. I don't know actually exactly how it works now, but you can shine out, but you can
I was playing with fibre optic yesterday, and you were able to bend it, and the light just kind of goes whichever way you bend it. That was kind of fun.
Just one question. You said you can actually transmit for 150 kilometers without any attenuation?
Yeah.
So any at all, or?
Yeah, well, you have attenuation, sorry.
Without amplification.
Without amplification.
30 dB, right?
Yeah, so you have 0.2 dB per kilometers.
For 10 kilometers.
Yeah.
Okay. 0.2 per
No, per
Just a comment.
So like 100K will be 20 dB.
Just a comment from the wireless side of the world. I mean, it's true that of course you can transmit much more, without need of amplification, but there is a point of failure in the optical networks, that is if it breaks, then you have to repair it.
Yeah.
You don't have this with wireless, because it's free.
Yeah.
So,
You can't break
I mean,
this,
it's of course much less powerful, but in a sense it's more robust to failures.
Yeah, it is.
But they are meant for different things, actually.
No, of course. I mean, it's just, they are complementing each other. That's why we have.
I
agree.
For example, you don't have resiliency on a wireless network. I mean,
One is
unless your base station falls off.
You should the base station. Maybe it will not work that well. But
That's what I was saying. But the resiliency problem is much less in wireless, because unless you take the base stations down, you want to. Why not? You have fiber cuts. And then, I was in a conference, and I was asking the people from Deutsche Telekom. They were saying, they think it's so important because of fiber cuts. I said, come on, how many fiber would you cut in a year? I was like, you cut about 2 a day. So they get 2 fiber cuts a day, because people start excavating for different reasons. And then they cut them apart. Especially because things are not, were not built properly. There's no. If you were to decide now, okay, we'll build the infrastructure for underground things, you put everything into one hole. You put, water, you put electricity, you mix them. Electricity, fiber, you put on one side of the network, you know what it is, and you put everything there. But at the moment, there's one excavation on one side, another on one side. And if you ask, remember who's there, if you even ask Electron, give me a map of all your fiber. Say, no, we don't know that. You know some of it. No, I can't tell you all of it.
We find it with diggers. And can you patch a fibre cable if someone breaks it, or do you have to?
No. So that's the point. I said 150 kilometers, but it's kind of a cheat there, because 150 kilometers suppose that it's one fiber. Okay. Then what happens is that you're not going to have that. We had an optical connection from here to the access point of Trinity College, and there were 6 hops in between. We said, just how many 6 hops? And the reason is pretty much for routing. Okay. If I have a continuous fiber, then I need a fiber from here to here, I need a fiber from here to here. This is going to need a full mesh. But with this, basically our patch panel, all our fibers come to patch panel, and from that patch panel you can take different directions. So that's the basic reason why. But every time you do a patch panel, when you lose, even if you lose 1 dB, you basically lost 55 kilometers potential distance. So the truth is, a system, they build systems which can go about, I think you can actually go maybe even 3,000 kilometers without electrical regeneration. Okay, so without having to stop it, read the bits, and send again. But basically they're built on purpose, and they're amplified probably every 40 or 80 kilometers, maybe 60, depends on the system. They might, there's different types of expensive amplifier to reduce the noise.
How do the kind of relay, like the forwarding bits work? Is it kind of like the signal comes in and it just amplifies and forwards it? Or
Depends what kind of, so there's a different type of amplification.
Yeah.
So since sometimes, we see on the slides later, you can use optical amplification.
Okay.
Which basically means you get the signal, optical signal, and then you get the output. Higher, more powerful version of the optical signal. It's pretty much the same with the analog amplifiers.
Yeah. And I assume that noise in the signal is pretty much nothing.
Well, no, you see, there's nothing because it's kind of different. So you don't have, the amplifier doesn't have thermal noise, which is probably what you said you want in your amplifier, right? Because it's not frequency. But you have other issues there. Okay? So you have something which is called amplifier spontaneous emission. which you don't know the reason until I explain.
Mm-hmm.
But basically is that the amplifier, is basically due to the fact that this amplifier, what it does is that produces photons.
Mm-hmm.
And then there is a mechanism that by which, as the photon arrives, it gets duplicated. And it gets an exact copy of the photon that arrives there.
Mm-hmm.
So basically duplicated, but it's exactly the same phase and frequency. But then, among these, there are some of them which basically just scatter like that with no reason. Right?
Mm-hmm.
So basically, those are random photons, and those basically random photons are basically noise. If they are and then there's another thing, another problem you have in optics is that something's called shot. It's different type of noise, shot noise.
Okay.
So basically, this once you go to the receiver, then you have to see what's the noise that you have to receive. So it's an electric receiver at the end of the story. So we'll have thermal noise as well.
Okay.
But then at this frequency, the shot noise is actually important. But shot noise means is due to the fact that the photons are quite powerful. Right? So if I send a bit, so if I have to send like a pulse, I think this can be about 100 photons. Am I right? I think I heard you can detect about 100 or 200 photons. If I send an electrical pulse, there's like a billions photons is there. So basically, there's so many that you can't see them individually. But in optics, it's like, imagine that the electrical pulse is like a wave made of water, and each photon is like a molecule of water.
Yeah.
So basically, you see the whole thing coming together, and I spread this one. If you have optical photons, instead of molecules, it's like you have little balls. Okay, so the same pulse you have about 100. So it's like having little balls, and these balls have a kind of a probabilistic nature because of they follow quantistic laws. So basically, they are probabilistic. So there is a probability that some of them arrive before the other, and that's the distribution noise as well.
Okay.
It is interpreted as noise. Now, fiber fundamentals. So the idea of the optical link is to transmit information from one side to the other side. And since our processing equipment does not work on optical, all processing equipment or digital equipment is always working on electrical stuff. You will have something electrical, it goes on optical, it gets transmitted, and then it gets reconstructed in electrical. Now, as you transmit anything, there are four fundamental impairments that you have to take care of. One is attenuation, and there's dispersion, and there are nonlinearities, and polarization dispersion. Does that mean that we know at the moment are the main one affecting us at the moment? So the idea is that I want to transmit a signal from here to here, and I want the same signal to be detected. I don't want errors. Now this is what people use to judge how good is the transmission or how bad are the interference. So this is what is called an eye diagram. I don't know if you've heard about it before. So this kind of shows, when you decide, imagine this is a very simple operation. So here, if this high, like imagine this is the point you decide. If when you decide anything, the value you receive is around here, then you decide it's in 1 bit. If it's around here, then you decide it's at 0 bit. Now, of course, how you decide if something is in between? I think one of the rules is that you basically split this in half. So that everything which is below this is actually at 0, everything above this is at 1. And then where exactly is the line actually depends on some complex coordinates. Now the point is that that's the transmission, it looks really nice. So this is called the high of the letter. Then after they get transmitted, because of the impairments, that's what I receive. Now you can see that now even if I have something as a detection threshold somewhere here. Now there are bits that might be around this place actually here. Now it depends as well if I'm able to sample at the maximum point, or else something that is actually shifting a little bit. So it might happen that I manage to sample sometimes here. Okay. If I sample here, then there are a lot of bits who are basically close to the edge. And anything that is close to the edge, basically I have 50-50 chances of getting the one. So that's how our errors arise from the transmission. So as you see, like here, there's what is called the eye. Here is called hypernoise. It's really nice and open. That means it's really there probably very little errors in this. But this eye is kind of start getting close. And when it's close, basically it means like you are out of environment. You won't be able to have a good filter rate. Now let's talk. We talk about the attenuation. The attenuation is pretty obvious and is due to some, the reason why fiber is attenuated is not that obvious now. but it's due to a couple of phenomena. One reason for attenuation is that basically the glass will absorb some of the energy, will transform it in I think what's called phonons, which is basically some vibration of the molecules. And another reason is that there's still some kind of scattering, so that some photon basically will just be scattered out. So the second point is the dispersion. Now dispersion is really kind of big problem in physics. Now let's have a look at this model dispersion amplifier. Now for the model dispersion, so this means we are using multimode fibers, and we can still use reasonably well this model, which is based on ray tracing. Because I mean, this ray tracing is of course not an approximation, but here it kind of works still well. So imagine I light up the laser, and I have these two rays. One is green, and one is red. Okay, they're of course they're actually the same frequency. It could be. It's just the way they propagate. Now, how do you see? These two, for example, are two modes of propagation in the fiber. Now, the red comes from different angles, so it's refracted at an narrower angle than the green. So the red one will kind of bounce more times than the green one. So this what means? This means that the red one will go to a longer distance than the green one. Because I mean, the green one is going kind of more straight, the other one is constantly down. Since the speed of the transmission, because I mean, they are roughly the same frequency, and they are basically in the same medium. So basically, their speed is the same. But if someone has to go further, someone has to go further than the other, then one of them will be late. Now, that's exactly what happens because of the dispersion. Now, I mean, imagine I produce these pulses at the beginning. Okay? These pulses will be made of different modes, although they are similar frequencies. Now imagine that, I mean, anytime I light up a fiber, it's not one single line of photons going on the direction of the wall. Okay, whatever is the laser, with some LED, which is even worse, the light will kind of scatter. So basically, this will produce rays in basically every kind of direction. Some of those rays will be lost, so there is a kind of a coupling efficiency of energy. When I have a laser or an LED, and then I put it on a fiber, I never manage to put all the energy from the light source into the fiber. Some of them will be lost because it's reflected straight away. Some of them will be lost because basically you will be on one of those modes that basically falls over the fiber. So what happens then with the dispersion? Now imagine I have these spots, and spots is created by these different. Imagine now you have only two modes. One is red, one is green, one is red, and I mean you can't separate this mode of the spots. They're just all over the place. They start propagating, but then the red part basically slows down with respect to the green part. So what happens is that basically it's like I send a pulse like this, and then the red part is dragged out, and the green part is going faster. So basically what happens is that this pulse is going to spread. That's what happens. That's what causes dispersion. Now the problem is when I put it in a communication channel, right, where every pulse has its own time slot. If I have a 10 gigabit per second, and I have a modulation which basically is one on-off. Basically means each pulse means just straightforward a bit, because of high modulation. Then I mean if this is 10 gigabit, these are a frequency of 10 gigahertz, and these are a duration of I'm not sure how much. But you can calculate that. So basically I transmit them, if they start spreading because of dispersion, then when I try to detect them, they will be on top of each other. That's what's called the interstitial interference. So basically, I cannot make up anymore which bit is which, and that's create beta array. Now, an idea that people had to solve this problem is to introduce the graded index fiber. Now, imagine this is the fiber cross section. So this is the core, and this is the outside part, which is called the slab. So, step index fiber, so it's the one fiber we have seen so far. If I have to do a diagram, so here I have basically the distance from the edge of the fabric into the core and out to the other edge. And here I have the value of the reflective index. Right? So this depends on which material I put in there. So step index means basically it's flat, so as one value up to here, then it goes straight to another different value higher in the core and one, and then out of the core it goes down. This is the index. Now the idea is that people start introducing this fiber which is called gravity index. So basically it means that the transition here is not stepwise, but is kind of continuous transmission. So it's kind of, like you can see it here as well. Basically I went through, then the value doesn't change straight away here, but it kind of changes gradually up to a maximum here at the center, and then it goes back again. Now what happens here now? This was made quite cleverly because the red, so now the red light, the red ray is the one that advances more up and down. So it has a longer, basically has a longer way to go. But if you look at it, since he has a longer way to go, it advances more, he will spend more time at the edges with respect to the green one. Okay? So the green one kind of goes more straight. That means the green one spends much less time at the edges with respect to the red. And the red will spend more time at the edges. So if since this M1 basically tells me what's the speed of the light at any point. So basically, in this way, the center of the core is more affected, in the meaning that the light will go slower here because M1 is higher. While at the edge, the light will go faster. So basically, the red one now is still doing more well. It still have to propagate over a longer distance, but it spends more time on a region which is faster than the other one. So basically, if you twinkle with these values a little bit, then you get that the dispersion can actually be much less. And I'll show you later some kind of fibers that as I said before, this is very nice and easy to understand. The problem is that this, the small multiple fiber is probably the last point we can use this ray tracing things. Because as we go to single mode, we can't understand anymore just with this mode. Things become more complex. So the truth is that if you want to understand how light propagates in a fiber, you have to go to the maxwell equations. That's the only thing you can do. I'm not going to, I just want to show how people arrive to the solution using these equations, but I'm not going to them. So basically, you have the four basic equations, and then you have other kind of equations that will support this one. Not going to get to them. So these are very complex. Even a basic problem can be extremely daunting to solve those. But then what happens is that you can make simplifications. So at any stage you make simplification, for example. If you have a low frequency, then you can assume fields that are more static in simplification. Optical level you can also make simplification. I think microwave is actually point where you can make the least simplification. So microwave always the time to solve this. So for optical, you can simplify, for example, you use a silicon, which is glass, so you have a medium which is not magnetic, so M goes to 0, and that solves some of the question already. It's non-conductive, so the conductivity is 0, then the conductive current is 0, so you don't have that, for example, in microwaves. Okay. Microwaves you use close microwaves conductive, the medium you use. And then you might have no free charges in the medium, so basically you get a lot of simplifications. And what you do is that you take the whole equation, you mix them together, and you obtain basically this. By solving this, the solution of this, basically, which is, I'll show you in a moment, will give you a propagating wave. Okay? So anything that transmits in electromagnetic, in photons, is a wave. And a lot of things that transmit are actual waves, like even the voice transmission, which is a change of pressure in the air as well, that's coming more towards a wave. So to solve, for example, if you want to do it easy, you go to the frequency domain with the Fourier transform, so you have this relation, so the derivative becomes a multiplication, and this relation transforms into this one. Okay, so you don't have any derivatives anymore, just addition. So the solution basically, again, you make more simplification, linearity, it's linear, susceptibility, linear susceptibility, so it's then homogeneity, so the medium doesn't change depending on which way you do it. You come up with two equations, and C is the speed of light, and if you are in the vacuum, this will be the relation, or else it will change if you are not in the vacuum. And then this tell you how the different index is connected to the linear susceptibility, and so on. Omega is what's called the angular frequency, but this will come in waves, it comes quite often, but it's basically just 2pi divided by the wave. So they're all connected together. And this is an example of a linearly polarized wave. So this is the easiest way we probably could think of. So it propagates on this way, basically I think there is what's called the right hand thing. So you have the electric field is on one way, the magnetic field is on the other way, and then it means that it's going to propagate on this way. So you have an electric field which goes varies up and down as it propagates, and then the magnetic field is just perpendicular to it, it propagates this way. So these are the example solution. Now, what happens when you put this in the fiber? Okay? So basically what you have to do to understand what happens in the fiber in terms of anything, dispersion, propagation, and all that stuff. You basically, you have to try to solve the wave equation in the fiber. So basically you put the equation there, and then you just have to put some constraints, which are quite easy. You have two mediums here. Okay? So basically this value of n will be different. The rest will be the same. But then basically only put two continuity. You have to put some continuity constraints where you have to say that the fields, well, electromagnetic fields, I think, or either the magnetic fields, I don't know. One of the two is continuous here, while one of the others is allowed to be continuous on the edge. But anyway, even E or H must be continuous at this point. And then this is one equation. And then the second one is that you want the field to go to 0 as you go to infinity. And that basically tells you with this equation, so these constraints, you come up with an equation where there is all the solutions of this particular equation will tell you what's possible for anything to propagate in here. Okay, those solutions will become the modes of propagation of the fiber. I know it's big complex, but it doesn't So the wave equation basically are I think when you come up with a complete solution there and you solve the solution, those solutions are called modes, propagation modes in the fiber. Each mode has its own propagation characteristics and propagates a different speed. Now these are an example of how that looks like. So if you cut the fiber and on the cross section, for example, the first mode, basically you can see it like that. Okay? So basically there's it's a mode where you have most of the energy inside, and then as you go outside, it vanishes. And it vanishes pretty quickly once you go outside the door. I think in terms of 1 or 2 waves, something like that, it is completely gone. That says also why it's easy, but it's much more secure to have an optical communication than a wired communication. Because the wired communication, you can put some kind of antennas around it, and you can pick the signal up. While with optical, there's absolutely nothing you can do. Okay, because everything is, the whole field terminates here. So there's no way you can interact with that. So these are different modes. So if you go to the second mode, then you will see the fiber, there's energy on one side, energy on the other side, nothing in between. But usually what you have is a superimposition of all these modes. Now if you look at this tells you that it has a normalized frequency. So it goes from 0, 1 to 3, and this is how you find the normalized frequency, which basically depends on the wavelength, on the difference between the refractive index, and as well as the core of the fiber. So this is important because, one way of getting rid of modal dispersion, okay, besides the graded index fiber, that does something, okay, but it's still, you can only do some, a little bit of that, okay, because anyway it depends on other effects, and you can never cancel it completely. So another way of cancelling, not caring of the modal propagation, is if you were able to work at frequencies, normalized frequencies, where actually there's only one mode, propagation mode allowed. Okay. So this basically shows you all the solutions. So if I work where the normalized frequency is 4, then I'll have 1, 2, 3, 4 possible modes. And you can be sure that all of them at some stage will be excited. So the idea is that, there's kind of a nice window here, where I can only one mode of propagation can exist. So how can I use that? Well, the idea is that if you twinkle with the difference between these two, the core, the radius core, and the wavelength you're using, you can pretty much be sure that you manage to be in there. So what's the difference between a single mode and a multiple fiber for telecommunication? As I said, you can work with that in many ways, but then there are only some ways that result to be practical for that. Especially, I mean, in theory, you just change the wavelength, but then there are some wavelengths where you cannot build lasers for those wavelengths, or it might be too difficult to do that. So, but what people have used in telecommunication and have been quite successful, it basically is to change the mode propagation, well, change the type of fiber, but basically restricting the core diameter. Okay. So this is the multimode fiber. This is a typical example. So the cladding, the diameter of the cladding is 1 to 5 microns, and the diameter of the core is 62 microns. Single mode fiber basically was built by restricting the core to about 9 microns, while the outside remains the same. So this is what this maybe came about 25 years ago. And even at that time, people were not sure. Because I mean, for a telecommunication operator, it's kind of a big decision. Okay? At a certain point, you have to decide, all the fibers we are going to install will be single mode or multi-mode. And installing the fibers is a huge cost, but I mean, it's really dangerous to make a wrong decision. So, times ago, when these people actually built, deployed, and developed this fiber, there still were technical issues because, this is, I mean, 62 micron is small, but 9 is like extremely small. So then when people say, no, at the beginning they were not able to actually couple the laser with the fiber. Because I mean, it's basically you have to actually, once the people used to do it manually by picking, and I did this job before, and it would take me like about half an hour trying to put the fiber inside. And then someone does this on your table, and then it's another half an hour. So you basically have a power meter, and then you check this, try to maximize the power that you see. But there are local means, so it's basically, now they all come shipped already patched, much nicer. But that was the problem. But then, fortunately people decided, okay, we'll risk it from the implementation point of view, because this is going to be much better. And in fact it is. And we'll show later the characteristics. Now, going back to the path loss. So this diagram shows how is the path loss in the fiber, and it shows as well why people use some kind of laser, some zones on the fiber. So path loss is the amount of power that's lost in the propagation, and this will depend on the frequency of the wavelength used for transmission. So these basically, these are early fibers like from the 1980s. But just to tell you that I have the slides after also that shows the history, a little bit of history of communication. But the first fiber was, in the 60s or the 50s, the Bell Labs were not studying fibers at all. They were trying to do microwave communication with with basic guided propagation made out of wires and so on. And they were spent so much money on that. And that was terrible because basically any disturbance from the soil, you put them underground, but any kind of disturbance from the soil, you actually just bend them just slightly. And by bending them slightly, you have all model dispersion that comes up. So it was very disaster. And then there was only one guy who instead decided he was going to try and work with fibers. Now, building a fiber of that size, when you don't have the equipment to build it, it's actually very hard. It's very hard to do. How do you build a small, tiny filament that size? And then even worse, how do you build another filament on top of that? Just telling you that the way they start doing it was by throwing arrows through a thing of metal glass, and the arrow was pick the glass and shoot out, and basically create a tiny little filament like that. So that's the way they actually start doing the experiment. Then the initial problem of this was that the glass wasn't very pure. Okay? So you are transmitting to a medium which potentially can absorb light. But at the beginning, the absorption was so bad that it was about 1,000 dB per kilometer. Okay? So it was impossible. You couldn't think of any application. The only application people would think would be for cryptography. So you basically get a bunch of fiber. You get a bunch of fiber like that. You twist them whichever you want. And basically that means since each fiber basically follows its own direction, then if you look at something after you've twisted them, then what comes up as an image will be totally distorted. Yeah. So the idea is that you could use that to encrypt and then decrypt a signal like that. And in order to do that, you need this much probably of fiber. So even if it's such a high loss. But that was our application. And then we also realized that actually the application wasn't good at all because it was so easy to do it.
What happens at 0.95 and 1.4?
Yeah, and I'm not here now. So basically at that point people said, okay, that's not going to be any good. Until someone said, okay, if anyone managed to build a fiber which has a loss of less than 17 dB per kilometer, then that point is going to be affected. And that's basically just calculated the distance between nodal exchange and something like that. And say, okay, at this point it could be used. Or at least it would be better. We still have to be amplified, but it would be better than amplifying the electrical signal. But basically then at some stage they came up with a fiber of like 17 dB per kilometer, and then they improved and improved. Basically they have to make it purer and purer glasses. That's what the way to do it. So the area, as you see, it actually was, I mean, it was quite good. We were maybe at about 3.5 dB here, and lower loss here, and so on. We had some peaks. I think this is the oxygen of the water absorbing peak, it's called. And then, they improved they managed to build fiber which had less and less water inside, so the water peak absorption could actually go down. And basically, you see, that at this point, I mean, people started using already this when it was at this point, right? And then immediately they saw that they were actually kind of what they call windows. So the point where the absorption was smallest, they were called windows, and then say, we're going to transmit that. Now, this is called the first window, this is the second window, this is the third window. They started with the first window for the only reason that they could manage quite well to build lasers working at this frequency. That was the only reason, because it would be much better here. But at that point, they didn't have laser working well here. Even building laser was showing a lighter outdoors, but was total. It took so long to make a laser would actually work even one day without being burned. And then you want the laser to last for 5 years. So it took a lot of time. I mean, this is the direction. Then there is the second window here, and this has a good, so this is a bit higher loss, but has a good thing that it has very little dispersion, and I showed you the curve of dispersion. While then there is the third window, and that's where most optical transmission occurs at the moment. So third window have the lowest loss, 0.2 dB per kilometer at the moment, has some dispersion, but you will see later that will be advantage and disadvantage to that. But the absorption here is not much higher, but it's still 0.4, which basically means it's the double. So you go half the distance as far as easy as that. So fiber loss. So fiber, the signal, as it propagates, basically it drops exponentially with this law. Now, you see in communication, people use decibels of because everything here is exponential, but it's very hard to deal with exponential. For two reasons. One, it's hard to deal with exponential numbers, exponential loss. And the second reason is that there is such a huge range between what can be transmitted and what can be received of many order of magnitudes that it's much easier to work with decibels. And this is basically how you can apply. So if you do a 10 on 10 of this, and you do the same of this, you basically, this will be your output power in decibels, for example, and this, you start fiddling a little bit with this, so you can take the power out, and this becomes an addition, because the rule of the logarithm says if two things are multiplied, you can divide them, and then become an addition. Here becomes subtraction because you have a minus here. And then the second rule is that if you have anything in the exponential of a logarithm, you can bring it out by just multiplying. So you basically come up with this. And that basically tells you that the output power in dB, 10 over 10, is equal to the input power, again in dB here, minus the length of the fiber multiplied by this path loss coefficient in dB. And this is the relation between this alpha here and this alpha here. So basically, alpha is 0.2 dB per kilometer. You are going out of 30 dBm. You're going in at 30 dBm. You know how much fiber it is. You know what's the absorption of the fiber. It's just a straightforward multiplication, subtraction, and you know already what's the power of the output. So it makes it very easy. Let's look at the dispersion now. So dispersion in the fiber. So we've seen, I'll actually say here, we'll just try dispersion now. So we've seen before model dispersion, which basically was due to the fact that there are different modes that refract different angles from the fiber. Now there are kind of dispersion, and these are due to the fact that the refractive index n is not constant, but the value actually depends on the frequency of the signal. So that n that I said, okay, it's a certain value, and that's okay, n has a certain value. But the way the wave interacts with that n, it actually varies depending on the wavelength of the signal. So dispersion is measured in picosecond, like nanometer per kilometer. So basically, the dispersion tells you how much the pulse is going to spread out. Okay? So that's why it's measured like this. Basically, this tells you how many picoseconds will the pulse spread if that pulse has a certain nanometer of bandwidth, and I transmit it over a certain number of kilometers. And this basically is exactly what that value. So there's a coefficient which is the dispersion coefficient, which exactly expresses how many picoseconds a signal of 1 nanometer of bandwidth goes when dispersed when it is propagated for a kilometer. Now there are three types of dispersion. One is modal dispersion, we have seen before. One is the chromatic dispersion. And chromatic because it depends on the color of the signal, which means it depends on the wavelength of the signal. And then another one is the polarization of dispersion, which we look at later on that. So again, dispersion problem I showed before, I showed it again. So this time we will have different modes. Okay? I mean, I used colors before for the modes, so it's not really, it can be misleading because colors usually means different wavelengths, while in propagation modes it means different modes. But here is actually very well used. So this is my continuums of frequency of wavelengths. Okay? So I have a pulse which basically has a certain bandwidth. By having a certain bandwidth, we will not use just one frequency. Okay? We use another frequency. So if I put them in the time domain, I could transmit them, and as they propagate, basically, they disperse and then start going on top of each other. So if I hear I have 1, 0, 1, they propagate, I sample, I have 1, I sample again, I find the 1 instead of 0. So that's an error. That's how error generated. Now here is something that gives you an idea of how much is the dispersion effect in communication. So basically this is already built up. This table is already built up. It tells you what's the maximum bit rate you can send over what distance to have an acceptable bit error rate. I'm not sure on what bit error rate this would be. Maybe it was 10 times 9 or 10 times 6 or whatever. But basically, see, this is the multimode step index fiber. So if I take a step index fiber and I use it for multimode transmission, so you see that it's pretty crap. I mean, I can go only 10 kilometers for 1 megabit. I mean, 1 megabit I can go electric with that. 10 megabit I can do 1 kilometer. I probably can do that with a copper wire. So this is totally useless. But then you see, by using that multimode relatives that I showed before, you can actually, you can go to kilometers or 1 gigabit. You cannot do that electrically. So these are an advantage. But still, modal dispersion, this is the maximum I can obtain in terms of performance, but it's still so far away from single mode fiber. Right? Single mode, basically, I totally ignore the modal dispersion. Okay? The modal dispersion is gone. Now I have to deal with chromatic dispersion. But the effect of chromatic dispersion is much less than modal dispersion because now this performs so much better. So, for example, 10 gig, I can go about 40K. So if you use a single mode fiber before an impairment. And then again, with this single mode dispersion shifted fiber, which basically is a different version which helps the dispersion. And I have to picture that a bit now, later on. So with this, basically, you can go over 200 kilometers at 10 gig. Now, this is only for dispersion, okay? So you probably cannot go 200 kilometers because of power absorption. So you have to amplify it. But in terms of dispersion, you can go that far without chemical dispersion. So modal and chromatic dispersion. I said that modal dispersion has a big effect. Now chromatic dispersion is the second most important cause, and I've explained all that already. And this is the curve of dispersion for single mode fiber. So as you see, I was saying before, 1500. This is the minimum absorption. So this is the minimum where the fiber has the minimum loss, and I have dispersion coefficient of about 17 picosecond. Now the reason why people were using the other window is because if I use the other window, I actually have zero dispersion. Okay? So I mean, okay, it won't be exactly zero, but almost zero. So that kind of means, I can propagate a lot without having to care about the dispersion problem. But then so people start using that, but then they realize that dispersion is actually not that bad at the end of the point. Right? So they realize that because of nonlinear effect, dispersion is actually good. And I will talk about the nonlinear aspect later. I want to confuse you now. So, but now the second question was, okay, is there anything we can do to change this characteristic? So let's start studying why dispersion exists on fiber. And they realize that actually this dispersion is done by the sum of two elements. One is the dispersion intrinsic in the material. So I mean, and that's, in this way, there's nothing you can do unless you stop using glass, you use something else. But it took them so long time to find a good medium mass glass that was made that, not going to go anywhere away from this. But then there's another part, which is what's called waveguide dispersion. And the actual curve is basically done by the sum of the difference of the sum of these two. So the next step, they realized that they can actually play a lot with the waveguide dispersion. So waveguide dispersion depends on how, this basically is kind of what depends on how the mode, the propagation mode, it interacts with the two parts of the fibers. Okay, so what happens on the boundary between the core and the fiber? So this is the thing the fiber we used before. Now then they realize that if they start working and creating very strange shapes to the profile of the fiber where they meet, they can actually pretty much move this which way, up and down, and twist it wherever they want. So what they end up doing is that they end up building a fiber which is this one, which is called, this one is an normal fiber. And basically they build a fiber which is this one, or this one here. This is called dispersion shifted fiber. Dispersion shifted because the 0 point now, so the 0 point here before was 0. Now the 0 point is 0. It's exactly what I want for the transmission. There is another reason why, the reason why people want this transmission as well is that optical amplifier can only be built successfully in this region. If I work on this region, I can't amplify the signal optically, so it costs much more. So people really do want it to operate in this region. And they realize that they I can build things which has very little dispersion there. They start building a system with that, and then they realized, shit, if I put multiple wavelengths in there, the system becomes totally, it works fine if you put one wavelength, but with multiple wavelengths it becomes extremely bad. And the reason is because of nonlinear phenomenon that it's here, so I need to do it the other way. So then linear phenomenon, basically what happens, nonlinearity means that if I have one signal, I have a fiber, I transmit a signal, it's fine. The signal will go, there will be some nonlinearity as well. And now imagine I have a second signal. So if I transmit those two signals in the air, basically we'll be fine. Okay? If I transmit anything on the air, two signals can actually pass across each other without even know they exist. The only problem is that at the receiver, if they're on the same frequency, I'm going to confuse them. If those two signals are at a different frequency, I can't separate them. But the problem, if I'm on like vacuum transmission, if the signals start going crossing each other or travel on top of each other, there's no bother at all, as far as I'm able to detect them as different wavelengths. The problem is that if I put it on, I'm putting them in a material which is a fiber. So what happens, you can think this way, I put a signal, the signal propagates, but by propagating, it's going to change the characteristic of the fiber itself. Because even if it's a non-conducting medium, there's still electrons, protons in there. So any electromagnetic field I put anywhere is going to change the way that material looks like, at least on a scale. So what happens is that I send the signal slightly change the fiber, and I send the second signal sees the new version of the fiber. Now, of course, this actually happens reciprocally. But the point is that what happens is that I have one signal, the signal changes the characteristic of the fiber, but the signal goes like this. Right? So if I have a signal that propagates signal 1, the signal goes like this. is going to change the fiber. Going to change the fiber in a way that looks like that. So if I have a second, so this is signal 1, if I put a second signal 2, even if I put a second signal 2, which is like that, since this is kind of imprinting this kind of modulation of the fiber, okay? Because the fiber sees electromagnetic field as exactly like this, so it will respond to anything else. It's something like that. So what happens is that, if you send a flat signal, you will see that the signals start getting the same thing. So you kind of, there's a kind of, you kind of see that the signal can imprint on something else. So basically, if I have loads of them together, they all start modulating each other, create a mess. Now, it's much worse this if you have no dispersion. Okay? If I have no dispersion, I have signal 1, which is like this, and signal 2, which is, something different, which is like this. If I have no dispersion, these are two different frequencies. This will travel at exactly, so this will travel at exactly the same speed. Okay? So that means if they go about 80 kilometers away, they will always see, so this part here will always see this part. This part here will always be affected by this part and so on. So basically, it's like they're together for the whole time, and they have 80 kilometers of space to actually imprint each other. It's like if I try to imprint something, something soft. If I do it like this, you can barely see it. If I keep doing it for a lot of time, you'll see technically what happens there. So this is pretty much the same. So if I have no dispersion, then this travels at the same speed, and they have all the time to basically affect each other because they are not opposite. But then, so they realized this, and then what they did is that they built a different fiber, which is called non-zero dispersion shifted fiber. So basically, has a little bit of dispersion, okay, but it's not that much to affect the dispersion by the way. So I mean, what happens there is that if these two instead of dispersion, this will travel faster. So the effect, so this point here, for example, first will be affected by this, then by this, then by this, then by this. And if at the end they will be averaged all over, okay? And they kind of cancel each other, that's the main purpose. I don't think it will be very easy to understand this one. I mean, that's why they did that, the second fiber. Third, dispersion we said. So we talk about modal dispersion, chromatic dispersion. There's another one which is called polarization modal dispersion. Now, this is due to the fact that the fiber is basically a circle, okay? So it's totally symmetric. So for that reason, the solution, even of the single mode propagation, comes out that it has two components, okay? And these two components are basically perpendicular to each other. And I mean, these are, you can imagine them as degenerate modes. That's the way it is. So they are perpendicular to each other. Now, because of imperfection around how the fiber is built, it's not exactly symmetrical. So there could be one side which is different from the other. And then there are other characteristics that can cause this type of dispersion. For example, I mean, there are how much the fiber is stretched and so on. But what happens basically is that since the fiber is not exactly symmetrical, this mode that propagates with this sees certain characteristics of the fiber. And the mode that propagates with this sees kind of different characteristics. So what happens basically is that they travel and swoops, this one goes faster than this one. At the end, I mean, as you don't detect the different polarization, at the end what happens is that the signal basically is wider. And that's exactly what happens with dispersion. It doesn't really matter if they are wider this way or wider this way. At the end, you detect the photon source. Anyway, this is much less severe than chromatic dispersion, so the people only start carrying on this as they start building system of 40 kb per second. So the other effects I was talking about are nonlinear effects. I already told you roughly why that happened, for example, in the fiber. There are different kinds of nonlinear effects. One is called phase modulation, and basically, so the one I told before was cross-phase modulation. Okay? So basically one signal affecting the fiber and then modulating the other signal. Okay? So creating that, basically this you can see it in different ways. Another way of seeing is that this creates a change in the factor index, and other fibers see a change in their factor index. That's modulated by that. There is set-phase modulation, which basically is the same as this, with the fact that a signal can do it also to itself. So I propagate, I'm changing the fiber, therefore I'm seeing a different thing. Right? And depending on what signal I put, I see this difference. So if I'm modulating in amplitude, for example, there will be some moment that the fiber is affected, some moment the fiber is not affected, and so on. And this is basically I do it on a circuit. So both of these create a broadening of the pools, and basically they just create more dispersion. There's another phenomenon as well, it's called forward mixing. Now there's more than this, they're all kind of scattering phenomena, but they just not more. Just mentioned forward mixing, which basically is, again, since the refractive index basically is the thing that can make signal multiply each other. So what happens is that you can actually, if you have a number of frequency of wavelengths in the system, new wavelengths can actually be generated from nothing. So you can see this very well if you start multiplicating the sinus of omega multiplied by sinus of 2 omega, and then you see that as to be multiplied this sinus wave, you basically create new waves which are either the difference or the multiplication of this. And that's the effect. That's not right. I think probably okay. I go again. So this is a little bit of history of optical communication, but I already told you about it a little bit. So I mean, everything started with the lasers in 1960. I mean, the laser was built theoretically years before, but no one managed to build one until here. And then, so then I was saying that people started creating fibers, but then there was a concept of building a fiber with less than 20 dB. That was quite important because to get people attacked. You have to get better than this if you want this to work. And then first fiber came at 17 dB per kilometer in 1970. And this the guy who built this fiber was called Corning glass, something like that. And they're actually still doing that. Then see this is the Internet over traffic, and this is the new conventions we have. So here the lowest fiber, the first link is in 1977, first optical link ever built. It became a submarine cable in 1980. The only difference was you have to make sure that water would break. And then in the meantime, this is the became in 1980, so it was building as well. Worldwide in 1993. And you see both this and this start making this grow. Actually, I mean, this now is logarithmic, okay? So every time you go 10 times. And I mean, really, the importance, I mean, at this point, you could still send internet over old, like copper connection and so on. But it became special at this point when we had optical amplifier and especially the EDFA, which is a particle amplifier, and the WDM, which basically means put more wave in the same system. They actually don't think it out. And it's actually here, so this is 1996, the first transatlantic WDM was 1998, and that's in 2000 that the internet surpasses voice. Because I mean, of course, if you didn't have so much bandwidth, there's no way you could. I mean, you have to pay probably to pay 100 euro every time you go to Facebook. You wouldn't do that. And that was it. And then switches for 2000, G-Phone 2003, and DSL 2000. Okay, actually this is important. So in Japan 2007 there were more fiber connections.